First construction in Regents Review number 3 is to construct a segment that is a quarter the length of segment AB that they give us here. So in order to first cut a segment in half, we need to do a perpendicular bisector construction. So I'm going to open up to one endpoint, and it doesn't matter the exact length I use. I just have to be more than 3/4 down the line segment. You could even open up all the way to B if you'd like. But then whatever measurement you used on A, when you go over to B, and this is really hard on the computer without changing the measurement. When I go over to B, I have to make sure that I'm using the same measurement, so I split it equally. And that's how you get a perpendicular bisector. Once you connect, I don't like that line. Let me get a solid line. Once you connect through the intersection points with your straight edge, you have a perpendicular bisector. So this is splitting line segment AB into two congruent pieces, from A to the midpoint over here, and from the midpoint to B. So this is splitting it halfway. We need a quarter of the way. So in order to get a fourth from a half, if you half a half, you get a fourth. So all I need to do is cut one of these halves in half. And I'll just cut this half over here in half, the one on the left. So I'm going to put my compass back on point A, and let me get a different color so this is easier to see over here. And what I'm going to do is now, instead of using B, I'm going to use the endpoint of the line segment I'm cutting in half, which is from A to the midpoint of the line segment that we just found, because we're having the half. So our two endpoints are one of the endpoints and the half. And then I'll make my arc. And notice I opened up all the way to the other endpoint. As long as it's more than halfway down the line segment, it doesn't even matter where you open it up to. And then I'm going to make another arc over here. And you can make full circles too. It doesn't even matter. It all works. And then I'm going to connect right through my perpendicular right through my intersection points. And here's my perpendicular bisector. So now I have split the half into two equal halves. And we need a segment that's a quarter AB. So this is a quarter. This is a quarter. It doesn't matter which one. I'll just indicate this one over here. Yeah, it just says construct a segment that's 1/4. I'll just label it like it is in the picture. I'll just label it C. You don't even have to label it. There we go. C, just like in the picture. But that's the line segment we're looking for. It doesn't matter if it was over here, if it was over here, if we have this half, right? As long as we're having a half, then we have the correct construction here. Okay, we need to construct the line of reflection. So remember, when we reflect, things are equal distances on both sides of the line of reflection. So guess what we're going to be doing to create equal distances? Another perpendicular bisector construction. Anytime we have equal distances, perpendicular bisector. So what I'm going to do is I'm going to connect a pre-image and an image point together. They have to correspond, so just make sure that you are taking a pre-image point and its corresponding image point in the same spot on the other triangle. And I'm going to do a perpendicular bisector, just like we were saying. Okay, and here we go. I'm going to go over to the other endpoint. And right through that intersection, I have my perpendicular bisector. Now, in order to be super accurate, you should really do this for also another pair of corresponding points as well. So I'm also going to do it with the corresponding points C and F, and I'm going to do the perpendicular bisector of that segment as well. Once again, it doesn't even matter where I open up to. As long as I'm doing the same thing on both sides, it does not even matter. Okay, and then here. And it's a little bit inaccurate because I am on the computer, but these two lines should completely overlap. because it should be the same line of reflection no matter which pre-image and image you do it for. So yours will be more accurate than mine because I'm doing it on the computer. But if you did it for two pairs of corresponding points, which you should in order to be completely accurate, it should overlap and it should be the same exact line of reflection because there's only one line of reflection to get this one onto this one. Okay, let me get a new compass. For this one over here, it says an isosceles right triangle. So I'm going to need equal sides, two equal sides for that. And I'm going to have to make CA perpendicular to CT and CA congruent to CT. Okay, so this one is a little bit tricky here. CA congruent to CT. Okay, got this. So I'm going to start with the perpendicular part, with the right angle part. So what I'm going to do is I'm going to make a perpendicular line through point C. I'm actually not going to do a perpendicular bisector like it says over here. And the reason for that is I don't need to bisect a line segment. I need to end up with a triangle with two equal sides, and they have to be the same length as CA. So what I'm going to do is I'm actually going to just measure CA, and I'm going to copy that measurement to the other side CB. But what I do need is I need a right angle right over here at point C because it says CA is going to be perpendicular to CT. So I imagine CT is going to be going this way, a vertical line right over here. They're going to be equal to each other because it's isosceles, but there's going to be a right angle right here. So what I need is I need the perpendicular line to go through point C. I'm actually going to be doing perpendicular lines through a point construction. So in order to do that, I'm going to put my compass on the point that I want the line to pass through, which is point C. And it doesn't matter how far I open it. All that matters is that I need to intersect the line segment in two spots. Now you might say, well, you didn't intersect the line segment in two spots. It's only intersecting it in one spot. That's okay because I can, for the purposes of my construction, I can extend with my straight edge the line segment over here. And I recognize that that's not actually going to be part of my triangle. That's why I put it as a dotted line over here. You could just put it as a lighter line or something, indicate it's not actually part of your triangle. But just for the purposes of my construction, it allows me to see, oops, that we have the intersection point over here and we have the intersection point over here, which we need. Okay. Now what I'm going to do is I'm going to put my compass on each of those two intersection points. I'll put that on this one first. Open up a little wider, doesn't matter how much. I just don't want it to get messy, so I'm going to just open up a bit wider so it doesn't like overlap into this arc. It's okay if it does. I just don't like it to be that messy. So I'll open it actually a little bit more. And what I'll do is I'll just make an arc, any arc, it doesn't matter. But whatever I do on this intersection point, I'm going to do the same thing on this intersection point without changing the width, the distance, or if you're using the flat red compass, the hole that you're using. And if you connect right through the intersection point, let me get a different line. I don't want the dotted line anymore. If I connect right through the intersection point, oh no, I don't want that dotted line. There we go. It does not want to stay red now. Okay. It should end up going right through point C, or at least close to going right through point C, like mine is. The thing is, I don't know where to stop drawing the side of my triangle. Do I stop here? Do I stop here? Do I stop here? I don't know. Because what I do know about the side is it has to be the same measure as CA, right? If this is CT, it does say in the question that CA and CT are going to be congruent to each other. So in order to make sure that they're going to be congruent to each other, I'm going to now measure CA so I can make sure that CT has the same measurement. We call this copying a line segment. So I'm going to put my compass on point C and I'm going to open up to point A so I can see how big it is. Then I'm going to take that measurement and I'm just going to use it to mark where the side CT ends. And then this point over here, I can label as point T. And that's all I need because now I can just connect T to A. And then I have triangle CAT. And I have a right angle right over here at point C because we did the perpendicular line through a point construction. And I also know that it's isosceles with CA congruent to CT because I did measure the length of CA and copy it to CT. Okay, here we need to construct the altitude. This is one that we've done in class recently. Let me get another compass. Where did my compass go? There it is. Okay. Okay, so it says the altitude from point C, and this is not a perpendicular bisector, so this has to change over here. This is not a perpendicular bisector. This is a perpendicular line through a point. In fact, an altitude is not a bisector necessarily. An altitude is just a perpendicular line through to a side of a triangle through the opposite vertex. It does not necessarily have to bisect. If it did bisect, it would not be an altitude. It would be a perpendicular bisector. So an altitude does not bisect. So I'm going to put my compass on the point that I want the altitude to pass through, which is point C. Okay, let me try to get that on as best as I can. Then, same construction as the previous one, perpendicular line through a point. All I need to do is make an arc that intersects, oh no, I made that too wide. It has to intersect the side of the triangle in two spots. So I want to be able to see that. Still too wide. Let me try a little bit shorter. That should, no, I'll get it eventually. There we go. We just want to intersect at two spots. So once again, my compass was on point C, and I just drew an arc that intersected the side of the triangle AB in two spots. And all I need is those 2 points of intersection, this one over here and this one over here. I'm going to try to darken them so I could see them a bit better over here. And now I'm just going to place my compass on each of those points of intersection, and I'll make an arc. And whichever I did on that point of intersection, I'll just have to do the same one on this point of intersection. And once again, yours is going to be more accurate than mine because on the computer, this is really annoying. But through the point of intersection, it should come really close to passing right through point C. Mine came out pretty good. And what this is it is an altitude. It is a perpendicular line to the side of the triangle AB that passes through the opposite vertex of the triangle C. It does not bisect. I cannot say this is equal to this. In fact, they do not look equal. It is not a bisector. It is just an altitude. Okay. Now we need to do an angle bisector. So this needs to change too. This is supposed to be angle bisector construction over here. So the angle bisector of angle ABC. So that's this angle right here. So in order to do that, I'm going to put my compass on the vertex of the angle that we're bisecting, which is angle B, angle ABC. And I'll just make an arc. It doesn't matter how big I make it. The only thing that matters is that it has to intersect the angle. So angle ABC in two spots, which it does, because this is angle AABC. I'm going to put my compass on one of those intersection points, just going to open up a little bit wider, make an arc, and then I'll move my compass over to the other intersection point, and I'll make the same arc using the same distance because we're bisecting. So whatever we did on this one, we have to do the same on this one to keep it equal. And then if we connect, starting at the vertex through the intersection point, we have our bisector. Since it does bisect the angle, it splits the angle into two congruent pieces. If I label this point over here point D, I could say angle ABD is congruent to angle CBD. In the next example, we're dilating the triangle by a scale factor of 2 centered at point C. So if it's centered at point C, it means point C is not going to change position. Point C is going to stay where it is because the center of dilation stays where it is. Whenever you center a dilation or a rotation around like a certain point, that point always stays put. So C is going to stay in the spot that it's at. Now, when you're doing a dilation, what that means is that you are taking the points, and if it's a dilation greater than one, like two, like we have here, you're making the shape bigger. And the way that you make it bigger is by taking the distance that the point is from the center of dilation. So the distance that B is from the center of dilation and doubling it. So you're taking point B and you're moving it further away from the center of dilation. You're moving it double the distance from the center of dilation that it currently is right now. So something important about dilations is that the center of dilation, the pre-image point, so B is a pre-image point, and the image point, so B prime, will all be collinear. That means they'll all be located on the same line. The only thing is I don't know how far along this line B prime will be located, so now's where I'm going to have to measure. But you should use your straight edge and just draw a line going far, so that way you know that B prime needs to be somewhere on that line. So what I'm going to do is I'm just going to measure. I'm going to measure from the center of dilation to point B. Once again, yours will be more accurate than mine. The computer is very, very, very annoying. Okay, and I'm just going to put a little arc to indicate that I measured. Because on the Regents exam, if you don't put an arc to indicate that you measured, or on the test even, no one knows that you used a compass, right? You know you used a compass, but nobody else does. So the way that people know that you used a compass is by your arc. So always leave your arcs, never erase your construction marks. So the distance from C to B was a scale factor of 1. It's what it is, right? So if I want a scale factor of 2, I just got to double it. And there we go. Here's point B prime. And it is double as far from C as B is. Next, we will do point A, and we'll find A prime. So once again, point C, A, and A prime are all collinear. They all lie along the same line. The center of dilation, the pre-image, and the image are all collinear with the dilation. So what I'm going to do is I'm just going to measure from point C, point A, to get that distance as best as I can. And I'll put a little arc to show that I measured that. And then I'm doubling the distance because I have a scale factor of 2. So I'm going to come on over there, and I'm just going to double the distance. There, that looks pretty good. And I'm going to call this point over here A prime. And A prime is double the distance away from point C as A is. And the last thing I'm going to do is I'm just going to connect all our image points together. I'll just use blue. So I'm going to connect C to B prime. Because remember, C is C prime. It just stays the same as the center of dilation. I'm going to connect B prime to A prime. And I'm going to connect A prime to C. And now I see my dilated triangle. Notice it has C as its center of dilation. That's why it looks like the original one is inside of the larger one, because they both have the same center. It's one of its points. So it's dilating around that center. And notice how the bigger triangle looks like it's double the size of the original, and that's because it is due to our construction where we copied the distance from the pre-image to the center of dilation, and then we doubled that distance. Over here, we're going to be making a line parallel to the given line through point C. And I'm going to be doing this one by making 2 lines perpendicular to the same line. Because if 2 lines are perpendicular to the same line, they are parallel. So first I'm going to make a perpendicular line through point C. So the way I'm going to do that, and we've done this before in this video for other constructions. Let me just get my compass oriented a good way. Is I'm going to put my compass point on point C. And all I want to do is make an arc that intersects in 2 spots, the line. So I have this intersection point here and this intersection point here. So what I'm going to do is I'm going to just take my compass over to each of those intersection points. It doesn't matter what distance I use, but whichever one I use on this intersection point. I'm going to use the same one on this intersection point. And all I need to do is go until they intersect, because that's all I need where they intersect. And then I did not do that one good. Let me try that again. Right through the intersection point, we have our perpendicular line. And it should come, if it doesn't pass right through point C, it should come really close to passing right through point C. And sorry, that's a little crooked over there, but it's okay. It's because the computer is really annoying. Okay, so now we have a perpendicular line to the given line. And now it's time for us to make a parallel line to the given line. And the way that we're going to do this is we made a perpendicular line to this line. So now what we're going to do is we're going to make a perpendicular line to the line we just created. So I still want it to pass through point C. But this time, instead of making an arc that intersects AB in two spots, I want to intersect my new line that I just created, this blue line, in two spots, which I just did. So now I have my two intersection points. Let me dot those for you. This one over here, and this one over here. Okay, now same process as before. I'm going to take my compass, and I'm going to go over to one of those intersection points. And it doesn't matter the distance I open it up to, but I just don't want it to look messy, so I don't want it to be in the arcs. And I'm going to make an arc. And then whatever distance I used, I'm going to use the same distance without changing anything in my compass. And I'm going to swing the same arc until they intersect. And right through here, through those intersection points, I'm going to draw my perpendicular line. It should go right through point C. And notice how it is parallel to the original line AB. And the reason, once again, that it's parallel to the original line AB is that right now what we have is we have two lines that are perpendicular to the same line. So they must be parallel. AB is perpendicular to this blue line. The red line is also perpendicular to this blue line. Since they're both perpendicular to the same blue line, they have to be parallel to each other. Two lines perpendicular to the same line are parallel. Okay, next construction, a 45-degree angle. So a 45-degree angle whose vertex is at point M. So not a bisector. We really don't want to do a bisector here. This is another perpendicular line through a point. It specifies point M, so we need to make our perpendicular line through point M. And this will give us a 90-degree angle. And once we have a 90-degree angle, we could just bisect it and get a 45-degree angle because half of 90 is 45. Okay, so I'm going to put my compass on point M, and we've done this so much now in this video. And I'm going to make an arc that intersects in two spots. Remember that we can extend the line if we need to see the intersection. Now I'm going to put my compass on each of those intersection points. And it doesn't matter the distance. I'm just going to make it a little bigger so I don't have arcs on top of each other. And just make an arc. And then over on the other intersection point, I'm going to make the same arc. And I just have to go until they meet each other. And right through this intersection point. Oh, I don't want the dotted line. Let me get the regular line. Okay, right through this intersection point. Just really wants that line. Okay. There we go. We have our perpendicular line through point M. So what we have created here is we have created a 90-degree angle, but we need 45. So all I'm going to do is I'm going to just bisect this 90-degree angle. So I'll just get rid of that so it's not confusing when I do the next part of the construction. Let me get a different color. Let me get my compass. So I'm just going to bisect this 90-degree angle. So to bisect an angle, you just need to put your compass on the vertex of the angle that you're bisecting. So I'm going to put it on the vertex of the 90-degree angle. And then all I need to do is make an arc that intersects the angle in two spots. And we have the 90-degree angle intersected in these two spots over here. because here's the 90-degree angle. So we intersected it in 2 spots. Now I'm going to take my compass and I'm going to just put it on each of those intersection points. Hopefully this is getting repetitive now, a lot of the same thing. And I'm going to just make an arc, and then whatever I did on one side, I'm going to do on the other side so it gets bisected. And then right through here, I'm going to start at the vertex and go right through the points of intersection. And what I have now is I have a bisected 90-degree angle, so each of these halves is 45 degrees. So I've now constructed not one, but actually two 45-degree angles here. Okay. Next one over here. So for the next one, we are once again doing a dilation construction. It's centered at B with a scale factor of 2. I'm going to skip this one because I just did a dilation construction with the same scale factor. So this one you will try on your own. And then this one over here, which I believe is one of the maybe not one of the last ones, we need to construct an equilateral triangle inscribed in circle O. So in order to do that, I'm going to just measure the length of the radius with my compass. First, we need to start with the hexagon construction. Okay, that's right here, so I'm in the right spot. So now that I have the length of the radius, I'm going to go over to point A. And mine is not going to be exact because it never is when I'm using the computer. And for this one, it's really easy to tell when it's not exact. And I'm just going to go over to each one. You probably remember doing this from first semester. And if I did this right, which I probably will not have it completely accurate on here, but you will probably have it a lot more accurate on your paper. When I cycle back around, I will end back up at point A. But on here, I probably won't. With the other constructions, oh, that's pretty good. Doesn't line up exact, but pretty good. It should line up exactly. For this construction, it's easier to tell if you're inaccurate. Okay, so instead of connecting all of these intersection points together, because that would give me the hexagon, just connect every other intersection point together. So I'm going to connect this one with this one, this one with this one, and there I have an equilateral triangle. So just connect every other intersection point. If you connect all the intersection points, you will get a hexagon. And you can make the full circles. You're probably used to seeing the full circles from semester 1, but I didn't want to make the full circles. Okay, so the best way to construct point D to make a parallelogram is actually not with parallel lines, because if you do it with parallel lines, it's going to be really annoying. It's actually with the fact that, and over here you see parallel, but that's really annoying. The fact also that opposite sides need to be congruent. So BC and AD need to be congruent. BD and AC need to be congruent. So I'm going to keep that in mind, because remember, one way to show you have a parallelogram is for opposite sides to be congruent. So I don't want to do more than I have to, because you could do parallel lines construction, but that one's hard for a lot of people. So I'm going to measure from A to C. And if you want, you could definitely connect those together so you could see them a bit better. Okay. And then I know that this distance has to be for BD. So I'm going to go over here and just use the same distance. Okay. And then I'll measure from B to C. Because remember, it's both pairs of opposite sides that need to be congruent. I'll just make an arc to show I measure. Remember, if you don't make your arcs, nobody knows that you measured. And then I'll go over to point A without changing my compass distance and use the same measure. And right here, where those arcs meet, that's point D. And once again, this is using the fact that both pairs of opposite sides are congruent in a parallelogram. You could also use the parallel line construction and use the fact that both pairs of opposite sides are parallel, but that is a lot more work. This is a lot easier. With constructions. With coordinate proofs, slopes are usually a lot easier than distances with finding the point. But with constructions, distances are often easier. What do we have to do here? Construct the diameter of a circle. This is a little preview for the next semester. I mean, the next unit that we're doing. But you can already see here, it's just going to be a perpendicular bisector from this chord to get the diameter. And once again, a little preview for next topic. I'm just going to do a perpendicular bisector. That's what it's showing me to do. I'm going to do that. And I'm going to keep the same distance on the other side over here. Don't want to change my compass distance. Okay, and then once I have my perpendicular bisector, I'm going to connect, oh no, I'm going to connect right through the intersection points. But I want to make sure that I extend the line all the way down. And the diameter of my circle starts over here and ends over here. If you want to highlight that, you definitely can. But I'm just indicating that this is the diameter of the circle. From one of these endpoints to the other, just the part that's inside the circle. Okay, now we need to construct a median to side AC. So in order to construct a median to side AC, I'm going to do a perpendicular bisector to get the midpoint, because median connects midpoint to the opposite vertex. So just a really, really, really quick perpendicular bisector here. Then I'm going to connect right through those intersection points. And careful, this is not a median, this is a perfect perpendicular bisector. In order to make my median now, and I'm going to do it in blue, I'm going to connect the midpoint to the opposite vertex. That blue line is the median. The red line's a perpendicular bisector. The blue line was a median. Okay, over here, we need to make a square that's inscribed in circle O. Real easy. All we're going to do, since diagonals of a square are congruent and perpendicular, because they're rectangles and squares, we're just going to do a perpendicular bisector. Once again, that's because the diagonals of squares are both perpendicular to each other and congruent to each other. Let me try that again. There we go. And let me get my straight edge. There we go. Now you might be wondering, where does the square come from? I'll do it in green. All you have to do is connect A to this point here, to B, to this point here, and back to A, and there's my square. Okay, here we have a hexagon. Let's do it. This is the same one as the equilateral triangle, except you're going to connect all at the end instead of just every other. So I'm going to leave you to try that one. You can watch the part about the equilateral triangle again if you need to. And finally, over here, we're going to construct the altitude from vertex J to ML. Going to put my compass on point J. And I needed to intersect ML in 2 spots. That wasn't wide enough. Let me try that again. Great. And now just go over to each of those intersections, just like we've done before. It's just a perpendicular line through a point. There we go. It should come really close to passing right through point J. And there we have an altitude to side ML of the trapezoid passing through opposite vertex J. Oh, and that's it. It's the end of our video over here, so I'll just leave it on this one over here.